Tonight, we're embarking on an extraordinary journey back to one of the most fascinating chapters in our planet's history. Whether you're a truck driver navigating the quiet highways under starlit skies, someone unwinding after a demanding day at the office, a student taking a well-deserved break from studies, or simply curious about the ancient world that existed beneath our feet, you've found the perfect place to rest your mind. Please, drop a comment letting us know what time it is where you are and which corner of the world you're joining us from. There's something magical about knowing we're all connected across different time zones, sharing this moment of wonder about our planet's distant past. Before we begin our adventure, I want you to know that while the visuals accompanying this journey will paint beautiful pictures of prehistoric landscapes, they're simply there to enhance your experience. You don't need to keep your eyes open to follow along. The story itself will unfold through words, allowing your imagination to construct its own vivid images of this ancient world. So settle in, get comfortable, and let's travel back approximately 250 million years to discover what our Earth looked like when all the continents were joined together in a single massive landmass we now call Pangea. Picture this. If you could somehow transport yourself back in time and float high above our planet during the late Permian period, you'd witness something absolutely breathtaking and completely alien to modern eyes. Instead of the familiar blue marble we know today, with its scattered continents separated by vast oceans, you'd see a world dominated by one enormous supercontinent stretching from pole to pole. This colossal landmass, Pangea, whose name means all earth in ancient Greek, represented the ultimate continental embrace, where nearly every piece of land on our planet had come together in a geological dance that had been choreographed over millions of years. The sheer scale of Pangea defies easy comprehension. Imagine taking every continent you know today, every familiar landform, and somehow fitting them together like pieces of an enormous jigsaw puzzle. The result would be a landmass so vast that if you started walking from one end to the other, the journey would span thousands upon thousands of miles across terrain that shifted from scorching deserts to lush wetlands, from towering mountain ranges to endless plains. This wasn't just large, it was monumentally massive, representing roughly 1/3 of the entire planet's surface area, concentrated into a single unified continent. But Pangea didn't exist in isolation. Surrounding this tremendous landmass was an equally impressive body of water called Panthalassa, meaning all sea. This global ocean was so enormous that it made our modern Pacific Ocean look like a mere pond in comparison. Panthalassa stretched endlessly in every direction from Pangea's coastlines, its depths holding mysteries and marine life forms that would seem utterly alien to our contemporary understanding of ocean ecosystems. The scale of this ancient ocean was simply staggering, containing roughly 90% of all the water on Earth's surface. Now you might wonder how scientists figured out that such a supercontinent once existed. It's not like there were any ancient geographers around to document Pangea's existence, and certainly no satellite imagery from 250 million years ago. The evidence comes from a fascinating detective story that spans multiple scientific disciplines, each contributing crucial pieces to our understanding of this prehistoric puzzle. One of the most compelling clues comes from the remarkable similarities we observe in rock formations across different modern continents. Geologists have discovered identical rock layers, formed under very specific conditions, appearing in places that are now separated by thousands of miles of ocean. For instance, distinctive red sandstone formations found in the deserts of the American Southwest share uncanny similarities with rocks discovered in the Scottish Highlands. These aren't just vaguely similar rocks, mind you, but formations that match down to their precise mineral composition, the way their layers are arranged, and even the microscopic details of their crystal structures. Even more fascinating are the fossil discoveries that seem to mock our modern continental boundaries. Paleontologists have unearthed identical species of ancient plants and animals in locations that couldn't possibly have been connected by any conceivable migration route across today's oceans. The Glossopteris, an extinct seed fern, provides perhaps the most famous example of this phenomenon. Fossils of this distinctive plant have been found in South America, Africa, Antarctica, India, and Australia. Now Glossopteris seeds were far too heavy to have been carried by wind across vast oceans, and the plant itself couldn't have survived in salt water. The only logical explanation is that these continents were once connected, allowing these plants to spread naturally across what we now think of as separate landmasses. The animal kingdom provides equally compelling evidence. Consider Lystrosaurus, a peculiar reptile about the size of a pig that lived during the early Triassic period. This herbivorous creature had a distinctive beak-like snout and powerful digging claws, adaptations that made it perfectly suited for a specific type of environment. Yet fossils of Lystrosaurus have been discovered in South Africa, India, China, and Antarctica. Given that this animal was purely terrestrial and couldn't swim across oceans, its widespread distribution only makes sense if these now distant continents were once part of a single connected landmass. But perhaps the most elegant evidence comes from studying the magnetic signatures locked within ancient rocks. As igneous rocks cool and solidify, tiny magnetic minerals within them align with Earth's magnetic field, creating a permanent record of both the field's direction and intensity at the time of formation. By analyzing these magnetic signatures in rocks of similar age from different continents, scientists can determine not only that continents were once connected, but also their precise orientations relative to each other and to the magnetic poles. It's like having a compass frozen in time, pointing toward magnetic north as it existed millions of years ago. The story of how Pangea came to be is itself a tale of unimaginable patience and inexorable geological forces. Long before Pangea existed, our planet's surface was broken into numerous smaller continents that drifted across the globe like massive stone rafts floating on a sea of partially molten rock. These continental masses moved at speeds that would make a growing fingernail seem rapid by comparison, typically traveling just a few inches per year. Yet over the vast expanses of geological time, these seemingly glacial movements could transport entire continents across thousands of miles. The process that brought these ancient continents together wasn't random or chaotic, but rather followed the predictable patterns of plate tectonics. Earth's outer shell consists of several large plates that fit together like pieces of a spherical puzzle, but unlike a traditional jigsaw puzzle, these pieces are constantly in motion, driven by the tremendous heat and pressure generated deep within our planet's interior. Some plates move toward each other, creating collision zones where mountains are born and continents merge. Others move apart, forming rift valleys and new ocean basins. Still others slide past each other in a sideways dance that can trigger devastating earthquakes. During the late Paleozoic era, roughly between 350 and 250 million years ago, several major continental masses began converging in what geologists now call the Alleghanian orogeny, the Hercynian orogeny, and the Uralian orogeny. These imposing scientific names describe mountain-building events that occurred as ancient continents crashed into each other with forces beyond human comprehension. When Laurussia, a northern supercontinent that included much of modern North America and Europe, collided with Gondwana, a southern supercontinent comprising South America, Africa, Antarctica, Australia, and India, the impact created mountain ranges that in some cases still exist today, though much worn down by hundreds of millions of years of erosion. The Appalachian Mountains of eastern North America, the Scottish Highlands, and parts of the Atlas Mountains in North Africa all represent scars from these ancient continental collisions. These ranges were once far more imposing than they appear today, potentially rivaling the modern Himalayas in their original grandeur. The tremendous pressures generated during these collisions didn't just push rock upward to form mountains, they also created entirely new types of minerals and metamorphic rocks, fundamentally altering the chemistry and structure of the materials involved. As Pangea took shape, its formation had profound implications for global climate patterns that would persist for tens of millions of years. The supercontinent's enormous size meant that vast areas of land were located thousands of miles from any ocean, creating the most extreme continental climate our planet has ever experienced. Imagine the difference between living near a coast, where ocean breezes moderate temperatures and provide regular moisture, versus living in the center of a continent the size of Asia, Europe, and North America combined. The interior regions of Pangea experienced temperature swings and aridity that pushed the limits of what life could tolerate. The presence of such a massive landmass also disrupted global ocean circulation patterns in ways that fundamentally altered how heat and nutrients moved around the planet. Today, our ocean currents form complex loops that carry warm water from equatorial regions toward the poles and return cold water toward the equator, creating a global conveyor belt that helps regulate climate worldwide. But with Pangea blocking many of these circulation patterns, the distribution of heat around the globe became far more uneven and unpredictable. During much of Pangea's existence, global temperatures were significantly warmer than they are today, with no permanent ice caps at either pole. This might sound pleasant, but the reality was far more complex and challenging for life. Without the moderating influence of polar ice, temperature gradients between different latitudes became more extreme, leading to violent weather patterns and seasonal variations that could spell doom for organisms that couldn't adapt quickly enough. The interior regions of Pangea developed into some of the most extensive desert systems our planet has ever seen. These weren't just ordinary deserts like the modern Sahara or Gobi, but continental-scale wastelands where sand dunes stretched beyond the horizon, and temperatures could soar to levels that would kill most modern life forms. The lack of nearby oceans meant that moisture-bearing winds rarely penetrated far inland, leaving vast areas completely dependent on whatever rain might fall during brief seasonal storms. Yet even in this seemingly hostile environment, life found ways not just to survive but to flourish. The fossil record from Pangean times reveals an astonishing diversity of organisms that had adapted to these extreme conditions in ways that continue to amaze paleobiologists today. Some plants developed extensive root systems that could reach down incredible distances to tap into underground water sources. Others evolved specialized structures for storing water during rare rainy periods, much like modern cacti, but often on a much larger scale. The animal life of Pangea was equally remarkable in its adaptations to continental living. Many species developed highly efficient kidneys that could extract every possible drop of moisture from their food, allowing them to survive in areas where drinking water was scarce or non-existent. Others became masters of estivation, a process similar to hibernation, but triggered by heat and drought rather than cold. During the harshest dry seasons, these animals would retreat to underground burrows or other protected spaces and enter a state of suspended animation, waiting for more favorable conditions to return. The plant communities of Pangea were dominated by groups that seem almost alien when compared to modern vegetation. Vast forests of seed ferns, which despite their name were neither true ferns nor modern seed plants, stretched across the wetter regions of the supercontinent. These plants had evolved a unique reproductive strategy that allowed them to thrive in the variable climate conditions that characterized much of Pangean geography. Their leaves were often thick and waxy, adaptations that helped them conserve precious moisture during dry periods. In the more arid regions, early conifers began to assert their dominance, developing the needle-like leaves and efficient water conservation systems that would eventually make them some of the most successful plants on Earth. These ancient conifers weren't quite like their modern descendants, but they shared many of the same fundamental adaptations that allowed them to thrive in environments where other plants struggled to survive. The animal kingdom during Pangean times was undergoing its own revolutionary changes. This was the era when reptiles truly came into their own, diversifying into an astounding array of forms that filled ecological niches we can barely imagine today. Some grew to enormous sizes, becoming the first truly gigantic land animals our planet had ever seen. Others remained small, but developed sophisticated social behaviors that allowed them to thrive in the challenging Pangean environment. Among the most fascinating inhabitants of Pangea were the synapsids, the group of animals that would eventually give rise to modern mammals. During the Permian period, synapsids were the dominant large land animals, including forms like the sailback Dimetrodon, which despite its dinosaur-like appearance, was actually more closely related to mammals than to any reptile. These animals had developed sophisticated thermoregulatory systems that allowed them to maintain stable body temperatures even in the face of Pangea's extreme climate variations. The late Permian period, which coincided with Pangea's peak formation, witnessed one of the most remarkable evolutionary radiations in Earth's history. Life seemed to be experimenting with every conceivable form and function, creating a biological diversity that in some ways exceeded what we see in modern ecosystems. There were herbivorous reptiles the size of elephants, carnivorous forms with saber-like teeth that could bring down prey many times their own size, and countless smaller species that filled every available ecological niche. But this incredible diversity came to a sudden and catastrophic end in what paleontologists now recognize as the most severe extinction event in Earth's history. The end Permian extinction, sometimes called the Great Dying, eliminated roughly 96% of all marine species and 70% of terrestrial vertebrate species. This wasn't just a bad year, or even a bad century for life on Earth. It was a near-complete reset of the entire biosphere, an event so severe that it took tens of millions of years for ecosystems to fully recover. The causes of this extinction remain a subject of intense scientific investigation, but most evidence points to a perfect storm of environmental catastrophes that made survival nearly impossible for most forms of life. Massive volcanic eruptions in what is now Siberia pumped enormous quantities of carbon dioxide, sulfur compounds, and other toxic gases into the atmosphere. These eruptions weren't brief events, but continued for hundreds of thousands of years, fundamentally altering the chemistry of both the atmosphere and the oceans. The volcanic activity triggered a runaway greenhouse effect that pushed global temperatures to levels not seen before or since in Earth's history. Ocean temperatures in some regions may have exceeded 104 degrees Fahrenheit, hot enough to kill most marine organisms and severely stress those that managed to survive. The oceans also became increasingly acidic and depleted of oxygen, creating conditions that could support only the most primitive and resilient forms of life. On land, the situation was equally dire. Acid rain fell regularly, stripping nutrients from soils and poisoning freshwater sources. The extreme heat and drought conditions that already characterize much of Pangea's interior became even more severe, expanding the uninhabitable zones until they covered most of the supercontinent. Plants died en masse, eliminating the foundation of terrestrial food webs and triggering cascading extinctions throughout entire ecosystems. Yet life, as it always seems to do, found a way to persist through even this ultimate catastrophe. The few species that managed to survive the end Permian extinction became the ancestors of all subsequent life on Earth, carrying within their genes the evolutionary innovations that would eventually lead to the rise of dinosaurs, mammals, flowering plants, and ultimately humans. These survivors were the ultimate champions of adaptation, possessing characteristics that allowed them to endure conditions that killed off the vast majority of their contemporaries. The early Triassic period, which began roughly 252 million years ago in the aftermath of the Great Dying, was a time of ecological rebuilding on a planetary scale. The survivors of the extinction event found themselves in a world that was essentially empty, with countless vacant ecological niches waiting to be filled. This created evolutionary opportunities unlike anything seen before or since, allowing surviving lineages to rapidly diversify and experiment with new ways of life. During this recovery period, Pangea was still largely intact, though the stresses that would eventually tear it apart were already beginning to build deep within Earth's interior. The supercontinent, during the early Triassic, was a harsh but gradually improving environment, with temperatures slowly moderating from the extreme highs of the end Permian extinction event. Rainfall patterns began to stabilize, allowing plant communities to re-establish themselves across previously barren landscapes. The first plants to colonize the post-extinction world were typically small, fast-growing species with simple reproductive strategies that allowed them to quickly spread across available territory. Many of these pioneer species were descendants of plants that had survived the extinction by growing in specialized microhabitats like caves, underground springs, or other protected environments where they could wait out the worst of the catastrophe. As plant communities recovered, they provided the foundation for the return of animal life. The first animals to reappear in significant numbers were often small, generalist species that could survive on a variety of food sources and didn't require highly specialized habitats. Many of these early Triassic animals showed signs of rapid evolutionary change, as natural selection worked overtime to help them adapt to the altered world they inhabited. One of the most significant developments during the Triassic recovery was the rise of the archosaurs, the group of reptiles that would eventually give rise to dinosaurs, pterosaurs, and crocodiles. These animals possessed several key innovations that gave them advantages over other reptile groups, including more efficient respiratory systems, improved locomotion, and enhanced sensory capabilities. During the Middle and Late Triassic, archosaurs diversified into an impressive array of forms, from small, agile predators to massive herbivores that rivaled later dinosaurs in size. The Triassic period also witnessed the emergence of the first true mammals, though these early representatives of our lineage were tiny creatures that lived in the shadows of their reptilian contemporaries. These proto-mammals had evolved from surviving synapsid lineages and possessed several crucial innovations that would eventually prove decisive in the evolutionary arms race. Their hair provided insulation that allowed them to maintain stable body temperatures. Their improved hearing helped them detect both prey and predators, and their more efficient metabolism gave them endurance advantages over cold-blooded competitors. Perhaps most importantly, these early mammals had developed sophisticated parental care behaviors that increased the survival rates of their offspring. While reptiles typically laid eggs and provided little or no care for their young, mammals nourished their babies with milk and protected them during their most vulnerable early stages of life. This investment in offspring quality over quantity would eventually prove to be one of the most successful reproductive strategies in the history of life on Earth. During the Middle Triassic, roughly 230 million years ago, Pangea was beginning to show the first signs of the geological stresses that would eventually tear it apart. Deep beneath the supercontinent's interior, convection currents in Earth's mantle were creating zones of weakness where the massive landmass would eventually fracture. These early rifting processes weren't immediately visible on the surface, but they represented the beginning of the end for the age of supercontinents. The climate during this period was still warmer and more arid than today's conditions, but it was gradually becoming more stable and predictable than during the chaotic early Triassic. Seasonal patterns were becoming more established, allowing both plants and animals to develop life cycles that took advantage of predictable wet and dry periods. This climate stabilization was crucial for the development of more complex ecosystems that could support larger numbers of species in increasingly specialized roles. The late Triassic, spanning from roughly 230 to 201 million years ago, represents perhaps the most fascinating period in Pangean history from a biological perspective. This was when many of the animal groups that would dominate later periods first appeared and began to establish the ecological relationships that would characterize life on Earth for the next 150 million years. It was during this time that the first true dinosaurs evolved, though they were initially quite small and relatively uncommon compared to other reptile groups. The early dinosaurs that appeared during the late Triassic were typically bipedal animals about the size of large dogs or small horses. They possessed several key innovations that would eventually allow their descendants to dominate terrestrial ecosystems, including hollow bones that reduced their weight without sacrificing strength, efficient respiratory systems that could extract more oxygen from each breath, and upright postures that gave them advantages in both running and walking. However, during their early evolutionary history, these features hadn't yet given dinosaurs a decisive advantage over other reptile groups. In fact, during much of the Triassic period, dinosaurs were relatively minor players in terrestrial ecosystems that were dominated by other archosaur groups, particularly the apatosaurs and phytosaurs. Apatosaurs were heavily armored herbivores that resembled enormous armadillos, some reaching lengths of over 15 feet and weights exceeding a ton. These impressive animals were covered in thick, bony plates that protected them from even the largest predators of their time. Their success during the late Triassic demonstrates that heavily armored defensive strategies could be just as effective as the more active approaches that would later characterize dinosaur evolution. Phytosaurs, despite their name suggesting plant-eating habits, were actually large, semi-aquatic predators that filled ecological roles similar to modern crocodiles. These impressive reptiles could reach lengths of over 30 feet and possess powerful jaws filled with sharp teeth, perfectly designed for catching fish and other aquatic prey. Their success in late Triassic ecosystems highlights the importance of aquatic habitats during this period, as rivers and lakes provided refugia where life could flourish, even when terrestrial conditions became challenging. The plant life of late Triassic Pangea was becoming increasingly diverse and complex, with the first appearance of several groups that would later become dominant components of terrestrial ecosystems. Conifers were expanding their range and diversifying into numerous specialized forms adapted to different climate zones and soil types. In wetter areas, extensive forests of tree ferns created lush canopies that supported complex communities of insects, small reptiles, and early mammals. One of the most significant botanical developments during this period was the evolution of more sophisticated seed dispersal mechanisms that allowed plants to colonize new territories more effectively. Some plants developed winged seeds that could be carried long distances by wind, while others evolved fleshy fruits that encouraged animals to eat them and disperse their seeds through their droppings. These innovations were crucial for plant communities trying to recolonize areas that had been devastated during the end Permian extinction. The insect world, during the late Triassic, was undergoing its own evolutionary revolution, with the appearance of several groups that remain important today. The first beetles were diversifying into numerous specialized forms, taking advantage of new ecological opportunities created by the recovering plant communities. Early flies were becoming important pollinators and decomposers, while primitive moths and butterflies were beginning to establish the complex relationships with flowering plants that would later become one of the most important coevolutionary partnerships in the history of life. But perhaps the most remarkable aspect of late Triassic ecosystems was their sheer complexity and the intricate relationships between different species. Food webs during this period included multiple levels of producers, primary consumers, secondary consumers, and apex predators, creating ecological networks that rivaled modern ecosystems in their sophistication. This complexity was all the more remarkable considering that it had developed in just 30 million years following the most severe extinction event in Earth's history. The marine environment surrounding Pangea during the Triassic were equally fascinating, though they remained quite different from modern ocean ecosystems. The vast Panthalassa Ocean was home to a remarkable diversity of marine reptiles that had evolved to fill ecological niches left vacant by the end Permian extinction. Among the most impressive of these were the ichthyosaurs, dolphin-like reptiles that had become so perfectly adapted to aquatic life that they could compete directly with sharks and other fish for prey. Early ichthyosaurs from the Triassic period were already highly specialized marine predators, with streamlined bodies, powerful tails, and large eyes adapted for hunting in dim underwater conditions. Some species developed the ability to dive to great depths in pursuit of prey, while others remained in shallow coastal waters where they could take advantage of the abundant small fish and invertebrates that lived near shore. The diversity of ichthyosaur species during the Triassic suggests that marine ecosystems were recovering rapidly from the end Permian extinction and developing the complex predator-prey relationships that would characterize later periods. Another important group of Triassic marine reptiles were the placodonts, unusual animals that had evolved specialized crushing teeth for feeding on shellfish and other hard-bodied marine invertebrates. These reptiles filled ecological roles similar to modern walruses or sea otters, using their powerful jaws to crack open the shells of mollusks, brachiopods, and other armored prey. The success of placodonts during the Triassic indicates that marine invertebrate communities had recovered sufficiently from the end Permian extinction to support specialized predators that could focus entirely on heavily defended prey types. The coral reefs of the Triassic period were quite different from their modern counterparts, being dominated by simple colonial organisms that hadn't yet evolved the complex symbiotic relationships with algae that characterize modern reef systems. These early reefs provided important habitat for a variety of marine life, including primitive sea urchins, early crabs, and numerous types of marine worms. While not as diverse as modern coral reefs, these Triassic marine communities were crucial stepping stones in the recovery of ocean ecosystems following the Great Dying. As we move toward the end of the Triassic period, around 201 million years ago, Pangea was beginning to experience the first major rifting events that would eventually lead to its breakup. The initial separation occurred along what is now the eastern coast of North America, as the North American and African portions of Pangea began to drift apart. This process wasn't sudden or dramatic, but rather a gradual widening of rift valleys that would eventually become the Atlantic Ocean basin. The early stages of Pangean rifting were accompanied by massive volcanic eruptions known as the Central Atlantic Magmatic Province, or CAMP. These eruptions were among the largest volcanic events in Earth's history, releasing enormous quantities of lava, ash, and toxic gases into the atmosphere over a period of roughly 600,000 years. The environmental impacts of camp volcanism were severe enough to trigger another major extinction event, though not as catastrophic as the end Permian extinction that had occurred 50 million years earlier. The end Triassic extinction event eliminated many of the dominant animal groups that had characterized late Triassic ecosystems, including most atosaurs, phytosaurs, and several other archosaur lineages. This extinction opened up new ecological opportunities that would be seized by previously minor groups, most notably the dinosaurs. In the aftermath of the end Triassic extinction, dinosaurs underwent rapid evolutionary radiation and quickly became the dominant large animals in most terrestrial ecosystems. The transition from the Triassic to the Jurassic period, roughly 201 million years ago, marks a crucial turning point in both the geological and biological history of our planet. Pangea was still largely intact, but the forces that would eventually tear it apart were gaining strength. The climate was becoming more humid and seasonal, supporting the development of lush forests that would provide food and habitat for the giant dinosaurs that would soon dominate terrestrial ecosystems. The early Jurassic period witnessed an explosion of dinosaur diversity that established many of the major groups we associate with the age of dinosaurs. The first giant sauropods appeared during this time, including species like Volcanodon and Barapasaurus, which represented the early stages of an evolutionary arms race toward gigantism that would eventually produce some of the largest land animals ever to walk the earth. These early giants were still relatively modest in size compared to their later relatives, reaching lengths of only 30 to 40 feet, but they established the basic body plan that would prove so successful for sauropod dinosaurs. Theropod dinosaurs also diversified rapidly during the early Jurassic, producing both small, agile predators and larger forms that could hunt the increasingly numerous herbivorous dinosaurs. The famous Dilophosaurus, with its distinctive double crest, represents one of the larger early Jurassic predators, reaching lengths of over 20 feet and possessing powerful jaws filled with sharp, serrated teeth, perfectly designed for slicing through flesh and bone. Perhaps even more remarkable than the dinosaurs themselves were the first pterosaurs, flying reptiles that had evolved the ability to achieve powered flight independently of birds, bats, or insects. Early Jurassic pterosaurs were typically small animals with wingspans of 3 to 6 feet, but they possessed all the anatomical innovations necessary for controlled flight, including hollow bones, powerful flight muscles, and sophisticated wing membranes that could be adjusted for different flying conditions. The plant life during the early Jurassic was undergoing its own revolutionary changes that would set the stage for the lush, dinosaur-dominated ecosystems of later periods. Conifer forests were expanding their range and diversifying into numerous specialized forms adapted to different climate conditions. In tropical and subtropical regions, tree ferns created dense canopies that supported complex communities of insects, small reptiles, and early mammals. The understory of these forests was often dominated by cycads, palm-like plants that produced large seeds that became important food sources for many herbivorous dinosaurs. One of the most significant developments during the early Jurassic was the evolution of more sophisticated plant-animal relationships that would become crucial for ecosystem stability. Many plants evolved chemical defenses against herbivorous insects and reptiles, while herbivores developed increasingly efficient digestive systems that could break down tough plant materials and detoxify harmful compounds. This evolutionary arms race between plants and herbivores drove much of the diversification we see in both groups during the Jurassic period. The marine environments of the early Jurassic were dominated by increasingly sophisticated marine reptiles that had evolved to exploit every available ecological niche in ocean ecosystems. Ichthyosaurs reached new levels of diversity and specialization, with some species developing enormous eyes for hunting in deep water, while others evolved long, narrow snouts for catching small, fast-moving prey in shallow coastal areas. The largest ichthyosaurs of the early Jurassic could reach lengths of over 30 feet, making them among the most formidable marine predators of their time. Plesiosaurs, another group of marine reptiles, were also diversifying rapidly during this period. Unlike the dolphin-like ichthyosaurs, plesiosaurs retained a more reptilian appearance, but were equally well adapted to aquatic life. Early Jurassic plesiosaurs included both long-necked forms that fed on fish and small marine animals, and short-necked varieties with massive heads and powerful jaws that could tackle larger prey, including other marine reptiles. The breakup of Pangea was accelerating during the Jurassic period, with new ocean basins opening up as continental fragments began drifting apart. The central Atlantic Ocean was widening steadily, separating North America from Europe and Africa. At the same time, rifting was beginning in other parts of Pangea, creating the foundations for what would eventually become the Indian Ocean and the southern Atlantic. These geological changes had profound implications for global climate patterns and ocean circulation. As new ocean basins opened up, they allowed for the development of more complex current systems that could transport heat and nutrients more efficiently around the globe. This improved ocean circulation helped moderate global temperatures and created more stable, predictable climate conditions that supported the development of increasingly complex terrestrial ecosystems. The Middle Jurassic period, spanning from roughly 174 to 163 million years ago, represents the golden age of sauropod dinosaurs. During this time, these giant herbivores reached sizes that still seem almost impossible today. Species like Camarasaurus and Brontosaurus achieved lengths of over 70 feet and weights exceeding 30 tons, making them among the largest land animals that have ever existed. The success of these giants was made possible by several key innovations, including highly efficient respiratory systems that could provide enough oxygen to support their massive bodies, and sophisticated digestive systems that could extract maximum nutrition from low-quality plant food. The ecological impact of these giant sauropods on Middle Jurassic ecosystems cannot be overstated. A single adult sauropod would have consumed hundreds of pounds of plant material every day, creating clearings in forests and influencing the distribution and evolution of plant communities across vast areas. Their enormous footprints created temporary ponds that provided habitat for small animals, while their droppings fertilized soils and dispersed seeds across the landscape. In many ways, these giant dinosaurs functioned as ecosystem engineers, shaping the environment around them through their daily activities. Predatory dinosaurs during the Middle Jurassic faced the challenge of hunting prey that could literally crush them underfoot. This led to the evolution of increasingly sophisticated hunting strategies and social behaviors. Some theropods developed pack hunting techniques that allowed multiple individuals to cooperate in bringing down giant prey, while others evolved incredible speed and agility that let them avoid the dangerous feet and tails of their sauropod victims while targeting vulnerable areas like necks and bellies. The most famous predator of the Middle Jurassic was Allosaurus, a 28-foot-long theropod with powerful jaws and sharp, curved claws that could inflict devastating wounds on even the largest sauropods. Fossil evidence suggests that Allosaurus may have hunted in coordinated groups, using teamwork to isolate and kill prey animals that would have been impossible for a single individual to handle. This represents some of the earliest evidence for complex social behavior in dinosaurs, foreshadowing the sophisticated pack hunting strategies that would later be perfected by smaller theropods. The late Jurassic period, from roughly 163 to 145 million years ago, saw Pangea continuing its gradual breakup as new ocean basins widened and continental fragments drifted farther apart. The supercontinent was no longer the unified landmass it had been during the Permian and Triassic periods, but rather a collection of large continental pieces connected by increasingly narrow land bridges. This fragmentation had important implications for the evolution and distribution of life, as populations of plants and animals began to become isolated on different continental fragments. One of the most significant developments during the late Jurassic was the evolution of the first birds from small feathered dinosaurs. Archaeopteryx, discovered in the limestone quarries of Bavaria, represents one of the most important transitional fossils ever found, possessing a mixture of reptilian and avian characteristics that clearly demonstrates the dinosaurian ancestry of modern birds. This crow-sized animal had teeth, a long bony tail, and claws on its wings like a reptile, but it also possessed flight feathers and other adaptations for powered flight that clearly identify it as a bird. The evolution of flight represented a major breakthrough that opened up entirely new ecological opportunities for vertebrates. Early birds, like Archaeopteryx, could escape terrestrial predators, access food sources that were unavailable to ground-dwelling animals, and colonize new habitats that had previously been occupied only by insects and pterosaurs. This innovation would eventually lead to the incredible diversity of modern bird species, but during the late Jurassic, birds were still a minor component of most ecosystems. Marine ecosystems during the late Jurassic reached new levels of complexity and diversity, with sophisticated food webs that included multiple levels of producers, consumers, and predators. The ammonites, spiral-shelled relatives of modern squid and octopuses, diversified into an incredible array of forms during this period. Some developed tightly coiled shells that provided maximum protection in a compact package, while others evolved loosely coiled or even straight shells that may have provided better swimming performance. The largest ammonites of the late Jurassic had shells over 6 feet in diameter, making them among the most impressive invertebrates of their time. The success of ammonites during the Jurassic period was partly due to their sophisticated locomotion system, which used jet propulsion to move through the water with remarkable speed and agility. They could adjust their buoyancy by pumping water in and out of chambers within their shells, allowing them to hover at specific depths or rise and sink as needed, while hunting for prey or avoiding predators. The late Jurassic seas were also home to some of the most spectacular marine reptiles ever to evolve. Leadsichthys, a massive filter-feeding fish, reached lengths of over 50 feet, making it one of the largest bony fish in Earth's history. This gentle giant cruised through ancient seas, filtering plankton and small fish from the water column, much like modern baleen whales, but achieving this lifestyle through completely different anatomical adaptations. Even more impressive were the marine crocodiles of the late Jurassic, particularly Geosaurus and its relatives. These animals had abandoned the amphibious lifestyle of their ancestors and become fully aquatic predators with shark-like tails and paddle-shaped limbs. Unlike modern crocodiles, which are primarily ambush predators that wait motionlessly for prey to come within striking distance, these marine crocodiles were active swimmers that pursued their prey through open water with remarkable speed and endurance. The transition from the Jurassic to the Cretaceous period, roughly 145 million years ago, marked another major milestone in Earth's history. Pangea was by this time well into its breakup phase, with the Atlantic Ocean continuing to widen and new rifts opening up in other parts of the supercontinent. The separation of South America and Africa was beginning, though these continents would remain connected by narrow land bridges for several million more years. The early Cretaceous period brought dramatic changes to terrestrial ecosystems, with the evolution and rapid expansion of flowering plants, or angiosperms. These revolutionary organisms possess several key innovations that gave them significant advantages over existing plant groups. Their flowers provided efficient mechanisms for attracting animal pollinators, their fruits offered effective seed dispersal strategies, and their broad leaves could capture sunlight more efficiently than the needle-like leaves of conifers. The rise of flowering plants triggered what paleobotanists call the Cretaceous terrestrial revolution, a period of rapid coevolution between plants and animals that fundamentally changed the structure and function of terrestrial ecosystems. Flowering plants provided new food sources for herbivorous insects, which in turn supported larger populations of insectivorous birds, reptiles, and mammals. The complex three-dimensional structure of flowering plant communities created numerous new microhabitats that could support specialized species with very specific ecological requirements. Dinosaur communities during the early Cretaceous were becoming increasingly diverse and specialized, with different species adapting to exploit the new ecological opportunities created by flowering plant communities. Ornithischian dinosaurs, the group that includes all the armored, horned, and duck-billed species, underwent rapid diversification during this period. Early members of groups like Iguanodon developed sophisticated dental batteries that could efficiently process tough plant materials, allowing them to take advantage of the abundant plant food available in early Cretaceous forests. Theropod dinosaurs were also diversifying rapidly, with some lineages becoming increasingly bird-like, while others evolved into massive apex predators that could hunt even the largest herbivorous dinosaurs. The early Cretaceous saw the evolution of several groups of small feathered theropods that were clearly experimenting with different approaches to flight and gliding. While most of these early experiments didn't lead to sustained powered flight, they represent crucial steps in the evolutionary pathway that would eventually produce modern birds. The marine environments of the early Cretaceous were characterized by rising sea levels that flooded large areas of the continental margins, creating extensive shallow seas that supported remarkably diverse marine communities. These epicontinental seas, as geologists call them, were perfect nurseries for marine life, providing warm, nutrient-rich waters where fish, marine reptiles, and invertebrates could flourish. Rudists, a group of unusual clam-like mollusks, became the dominant reef builders in many early Cretaceous marine environments. These remarkable creatures had evolved bizarre asymmetrical shells, with one valve forming a cone-shaped base that was cemented to the seafloor, while the other formed a lid-like top. Some rudists grew to enormous sizes, with shells over 3 feet tall, creating reef structures that rivaled modern coral reefs in their complexity and biological diversity. The continued breakup of Pangea during the Cretaceous period had profound effects on global climate and ocean circulation patterns. As continental fragments drifted farther apart, new ocean currents could develop, transporting heat and nutrients more efficiently around the globe. The expanding ocean areas also meant that a larger percentage of Earth's surface was covered by water, which tends to moderate temperature extremes and create more stable climate conditions. However, the Middle Cretaceous period, roughly 100 to 94 million years ago, experienced some of the warmest global temperatures in Earth's history. During this time, there were no permanent ice caps anywhere on the planet, and even the polar regions experienced subtropical climates. Palm trees and other warm weather plants grew as far north as Alaska and as far south as Antarctica, indicating truly global greenhouse conditions that were warmer than anything in human experience. These extreme greenhouse conditions were partly due to increased volcanic activity associated with the breakup of Pangea and the formation of new ocean basins. Massive underwater volcanic eruptions created new oceanic crust, while releasing enormous quantities of carbon dioxide into the atmosphere. At the same time, the warm, humid climate promoted rapid weathering of rocks on land, which released additional nutrients into the oceans and supported explosive growth of marine plankton communities. The abundant marine plankton of the mid-Cretaceous period created some of the most productive ocean ecosystems in Earth's history, supporting food webs that included everything from microscopic organisms to whale-sized marine reptiles. The chalk deposits that give the Cretaceous period its name were formed during this time from the accumulated shells of countless microscopic plankton organisms that lived and died in these productive seas. Life in the mid-Cretaceous oceans was dominated by marine reptiles that had reached unprecedented sizes and levels of specialization. Plesiosaurs evolved into two distinct groups: the long-necked elasmosaurs, which could reach total lengths of over 40 feet, and the short-necked plesiosaurs, which developed massive heads and powerful jaws that could crack the shells of the largest ammonites and other marine prey. The most impressive of the plesiosaurs was Leadsichthys problematic, a massive predator with a skull over 10 feet long and teeth the size of bananas. This apex predator ruled Cretaceous seas, much as great white sharks dominate modern oceans, but with size and power that dwarfed any modern marine predator. Bite marks found on other marine reptiles suggest that these giant plesiosaurs were capable of attacking and killing prey as large as themselves, engaging in underwater battles that must have been truly spectacular to witness. Mosasaurs, giant marine lizards that evolved from terrestrial ancestors during the Cretaceous, became increasingly important predators in later Cretaceous seas. These animals had evolved powerful swimming tails and paddle-like limbs that made them extremely effective aquatic hunters. The largest mosasaurs, such as Mosasaurus hoffmanni, could reach lengths of over 50 feet and possessed jaws powerful enough to crush almost any prey they encountered. On land, the late Cretaceous period witnessed the evolution of some of the most famous and impressive dinosaurs in the fossil record. This was the time of Tyrannosaurus rex, the ultimate terrestrial predator with a skull over 5 feet long and teeth designed to crush bone. But T. rex was just one member of a diverse community of giant dinosaurs that included equally impressive herbivores like Triceratops, with its massive three-horned skull and defensive neck frill, and Edmontosaurus, a duck-billed dinosaur that could reach lengths of over 40 feet and lived in vast herds that migrated seasonally across the landscape. The late Cretaceous also saw the evolution of some of the most bizarre and specialized dinosaurs ever discovered. Therizinosaurus was a massive theropod dinosaur that had abandoned carnivory entirely and evolved into a giant plant eater with claws over 3 feet long that it used to strip vegetation from trees. Carnotaurus was a predatory dinosaur with horns above its eyes and tiny vestigial arms that were even more reduced than those of T-Rex. Parasaurolophus possessed an elaborate hollow crest that could produce trumpet-like calls for communication across vast distances. The plant communities of the late Cretaceous were dominated by flowering plants that had diversified into forms very similar to many modern families. Oak trees, magnolias, roses, and even grasses had all evolved by this time, creating forest communities that would have looked surprisingly familiar to modern eyes. The rapid evolution of flowering plants during the Cretaceous had created the foundation for the complex terrestrial ecosystems that continue to dominate our planet today. But this golden age of dinosaur diversity was approaching its end. By the latest Cretaceous period, roughly 68 to 66 million years ago, several factors were combining to create increasingly challenging conditions for large terrestrial animals. Sea levels were dropping as the global climate began to cool slightly, reducing the area of productive shallow marine environments. At the same time, massive volcanic eruptions in what is now India were releasing enormous quantities of carbon dioxide and toxic gases into the atmosphere. The Deccan Traps, as these volcanic deposits are now known, represent one of the largest volcanic eruptions in Earth's history. The eruptions continued for over 1 million years, covering an area larger than Texas with lava flows over 1 mile thick in some places. The environmental effects of this prolonged volcanism were severe, causing acid rain, climate instability, and widespread ecosystem disruption that put enormous stress on both marine and terrestrial communities. Into this increasingly unstable world came the final blow, an asteroid impact that would end the age of dinosaurs forever. The Chicxulub impactor, roughly 6 miles in diameter, struck what is now the Yucatan Peninsula of Mexico with the force of billions of nuclear weapons. The immediate effects of the impact were catastrophic, creating earthquakes, tsunamis, and wildfires on a global scale, but the long-term effects were even more devastating. The impact threw enormous quantities of dust and debris high into the atmosphere, blocking sunlight and causing global temperatures to plummet. Photosynthesis virtually ceased for months or possibly years, causing widespread plant death and the collapse of food webs from the bottom up. The combination of impact, effects, and ongoing Deccan volcanism created environmental conditions that were impossible for most large animals to survive. The End Cretaceous extinction event eliminated roughly 75% of all species on Earth, including all non-avian dinosaurs, marine reptiles, and ammonites. This extinction marked the end of the Mesozoic era, the age of reptiles, and opened ecological opportunities that would be seized by mammals, birds, and flowering plants during the subsequent Cenozoic era. Yet, even as we contemplate this dramatic ending, it's important to remember that the story of Pangea and its aftermath represents just one chapter in the ongoing saga of life on Earth. The continental positions that resulted from Pangea's breakup continue to influence global climate patterns, ocean circulation, and the distribution of life today. The Atlantic Ocean that began forming as Pangea split apart is still widening by a few inches each year, while the Pacific Ocean continues to shrink as the continents slowly drift toward their next configuration. Scientists predict that in roughly 250 million years, the current continental arrangement will give way to a new supercontinent, sometimes called Pangea Proxima, as the continents complete another cycle in the grand dance of plate tectonics. When this happens, the Atlantic Ocean will have closed completely, and the Pacific will be reduced to a small sea, much as the ancient Tethys Ocean was reduced during Pangea's formation. But the future supercontinent will be a very different place from ancient Pangea. The life forms that inhabit Pangea Proxima will have evolved from the survivors of multiple extinction events, including the End Permian catastrophe, the End Cretaceous impact, and potentially other major disruptions that have yet to occur. The sun will be noticeably brighter than it was during Pangea's time, requiring different adaptations for dealing with increased solar radiation. The atmosphere may have a completely different composition, depending on the evolutionary innovations of future life forms. The story of Pangea reminds us that our planet is a dynamic, ever-changing system where life and geology are intimately connected. The massive continental movements that created and destroyed the supercontinent influenced evolution in countless ways, from the distribution of climates and habitats to the opportunities for species migration and genetic exchange. Understanding these ancient processes helps us appreciate the complex factors that have shaped the modern world and gives us insights into how life might respond to future environmental changes. The organisms that lived during Pangea's time faced challenges that are difficult for us to imagine, from the extreme continental climates of the supercontinent's interior to the catastrophic environmental disruptions that mark the boundaries between geological periods. Yet life not only survived these challenges, but used them as opportunities for innovation and diversification. The evolutionary experiments of the Permian, Triassic, Jurassic, and Cretaceous periods established many of the fundamental patterns and relationships that continue to characterize life on Earth today. The mammals that eventually inherited the Earth after the dinosaurs' extinction were descendants of small, furry creatures that lived in the shadows during Pangea's final stages. The birds that fill our skies today evolved from small, feathered dinosaurs that first took to the air when the supercontinent was breaking apart. The flowering plants that dominate modern terrestrial ecosystems began their rise to prominence during the Cretaceous breakup of Pangea's remnants. Even the deep ocean communities that exist far from sunlight in the abyssal depths trace their origins to the marine ecosystems that surrounded Pangea. The chemosynthetic bacteria that form the base of deep-sea food webs evolved techniques for extracting energy from chemical compounds during the extreme environmental conditions that characterized much of the Mesozoic era. These innovations allow life to flourish in environments that would have been completely sterile during earlier periods in Earth's history. The mineral resources that power our modern civilization also tell the story of Pangea's rise and fall. Many of our most important ore deposits were formed during the mountain-building episodes that created the supercontinent, as colliding continents generated the heat and pressure necessary to concentrate valuable metals in economically viable quantities. Coal deposits that fuel much of our energy production accumulated in the vast swamps and forests that covered parts of Pangea during the Carboniferous and Permian periods. Oil and natural gas reserves, which have shaped geopolitics and economics for over a century, formed from the remains of marine organisms that lived in the seas surrounding Pangea. The specific conditions of temperature, pressure, and organic content that are necessary for petroleum formation were particularly common during the Mesozoic era, as the supercontinent's breakup created numerous sedimentary basins where organic matter could accumulate and slowly transform into hydrocarbon deposits. The story of Pangea also illustrates the importance of rare, catastrophic events in shaping the course of evolution. While most evolutionary change occurs gradually over millions of years, the periodic mass extinctions that punctuated Pangea's history created opportunities for rapid diversification and innovation that might not have occurred under more stable conditions. The end Permian extinction that marked the supercontinent's peak formation eliminated competitors and opened niches that allowed the rise of dinosaurs. The end Cretaceous extinction that coincided with Pangea's final dissolution cleared the way for mammalian radiation and the eventual evolution of human intelligence. These insights from deep time have profound implications for how we understand and respond to current environmental challenges. The climate changes and biodiversity loss that characterize our modern era are occurring at rates that are rapid, even by geological standards. But the fossil record of Pangea's time shows that life has survived equally dramatic disruptions in the past. The key factors that determine survival during ancient crises, including adaptability, dispersal ability, and ecological versatility, remain relevant for species facing modern environmental changes. The breakup of Pangea also demonstrates the importance of connectivity and isolation in evolution. When the supercontinent was intact, species could potentially spread across enormous areas, leading to relatively homogeneous global faunas and floras. As continental fragmentation progressed, isolated populations began evolving in different directions, creating the biogeographical patterns we see today, where different continents host distinctive assemblages of native species. Australia's unique marsupial fauna, South America's distinctive mammalian communities, and Madagascar's extraordinary endemic species all reflect the evolutionary consequences of continental separation that began with Pangea's breakup. These isolated evolutionary experiments have produced some of the most remarkable creatures on our planet, from kangaroos and koalas to lemurs and tenrecs. The preservation of these evolutionary legacies depends on maintaining the habitat connections and ecosystem integrity that allow species to adapt to changing conditions. The ocean currents that regulate our planet's climate system are also products of Pangea's dissolution. The Gulf Stream that warms northwestern Europe, the Kuroshio Current that moderates Asian climates, and the Antarctic Circumpolar Current that isolates Antarctica in a ring of cold water all exist because continents are positioned in ways that channel oceanic flow in specific directions. As the continents continue their slow drift toward the next supercontinent configuration, these current systems will gradually change, with potentially dramatic implications for regional and global climate patterns. The magnetic field reversals that periodically occur in Earth's core, and which are preserved in the rock record of Pangea's time, continue to affect our planet today. These reversals, which can happen over periods of thousands to millions of years, temporarily weaken Earth's magnetic shield against cosmic radiation and solar particles. During Pangea's existence, life had to adapt to multiple periods of increased radiation exposure, developing various strategies for DNA repair and cellular protection that remain important for modern organisms. The atmospheric composition during Pangea's time was quite different from today's atmosphere, with generally higher carbon dioxide levels, and during some periods significantly reduced oxygen concentrations. The organisms that lived through these atmospheric changes evolved sophisticated biochemical mechanisms for dealing with varying gas concentrations and some of these adaptations persist in modern life forms. Understanding how ancient life responded to atmospheric change provides insights into how current organisms might adapt to the rapidly changing atmospheric chemistry of the Anthropocene. The soil systems that support modern agriculture have their origins in the weathering processes that occurred during Pangea's existence. The extensive mountain ranges created by continental collision generated enormous quantities of sediment that were distributed by rivers and wind across vast areas. These sediments formed the parent materials for many of the world's most fertile soils, including the black earth of the Ukrainian steppes, the alluvial soils of major river deltas, and the volcanic soils that support some of the world's most productive agricultural regions. The hydrological cycles that distribute fresh water around our planet were fundamentally different during Pangea's time due to the supercontinent's enormous size and the different configuration of ocean basins. The interior regions of Pangea experience some of the most extreme aridity in Earth's history, while coastal areas sometimes receive torrential rains from monsoon systems that dwarfed anything in the modern world. These extreme hydrological conditions drove the evolution of remarkable adaptations for water conservation and flood tolerance that can still be observed in the descendants of Pangean organisms. Plant communities during Pangea's existence developed the fundamental ecological relationships that continue to structure terrestrial ecosystems today. The evolution of complex root systems that could extend deep into soil and rock, the development of symbiotic relationships with fungi that enhanced nutrient uptake, and the creation of diverse forest canopies that could support multiple layers of life all occurred during the supercontinent's lifetime. These innovations established the basic architecture of land-based ecosystems that has persisted through multiple mass extinctions and continental rearrangements. The insect communities that pollinate our crops and decompose organic matter trace their origins to the diversification that occurred during Pangea's flowering plant revolution. The complex relationships between insects and plants that emerged during the Cretaceous period established pollination networks that remain essential for both natural ecosystems and human agriculture. Many of our most important food crops, including fruits, vegetables, and nuts, depend on pollination services that evolved during the later stages of Pangea's existence. The microbial communities that cycle nutrients through ecosystems and maintain soil fertility also underwent crucial evolutionary developments during Pangea's time. The extreme environmental conditions that characterized much of the supercontinent's existence drove the evolution of metabolic pathways that allowed microorganisms to extract energy and nutrients from previously unusable sources. These biochemical innovations expanded the range of environments where life could flourish and established many of the biogeochemical cycles that maintain environmental stability today. The symbiotic relationships that allow many organisms to thrive in challenging environments often originated during the environmental extremes that characterize Pangea's climate. The partnerships between corals and algae that build modern reef systems, the relationships between legumes and nitrogen-fixing bacteria that maintain soil fertility, and the collaborations between animals and gut microbes that enable digestion of complex plant materials all have evolutionary roots that extend back to Pangean times. The migration patterns of modern animals often follow routes that were established when continents had different positions during Pangea's breakup. Bird migration flyways, whale migration corridors, and the movements of land animals all reflect the historical connections between continents and the environmental gradients that existed when these behaviors first evolved. As climate change and human activities alter these traditional migration routes, understanding their deep historical origins becomes crucial for conservation efforts. The disease organisms that affect modern life also have evolutionary histories that extend back to Pangea's time. The pathogens that cause some of our most serious illnesses evolved alongside their hosts during the environmental stresses and population bottlenecks that characterized mass extinction events. The genetic diversity that allows some populations to resist disease while others remain vulnerable often reflects evolutionary responses to pathogen pressures that occurred hundreds of millions of years ago. The regenerative abilities that allow some animals to regrow lost limbs or organs, and which offer hope for medical applications, evolved during the challenging conditions that characterized life on Pangea. The ability to survive and recover from injury was crucial for animals living in the harsh continental climates and facing the large predators that dominated Mesozoic ecosystems. These biological innovations represent potential solutions to medical problems that continue to challenge human health and welfare. The social behaviors that characterize many modern animals, from cooperative hunting in mammals to complex communication in birds, often have origins that trace back to the ecological pressures of Pangean environments. The need to find resources in vast continental interiors, to coordinate reproduction in highly seasonal climates, and to defend against large predators drove the evolution of sophisticated behavioral strategies that remain important for survival in modern ecosystems. The sensory abilities that allow animals to navigate, find food, and communicate across vast distances evolved partly in response to the enormous spatial scales that characterize Pangea's landscapes. The echolocation of bats and dolphins, the magnetic navigation abilities of migratory animals, and the long-distance communication calls of many species all represent evolutionary solutions to challenges that were particularly acute in the extensive continental environments of the Mesozoic era. As we contemplate the vast sweep of time represented by Pangea's rise, dominance, and dissolution, we're reminded that our human species represents just the most recent chapter in an incredibly rich story of life on Earth. The 300,000 years of human existence is a mere blink of an eye compared to the 100 million year span of Pangea's existence, yet our species has already begun to influence global environmental systems in ways that rival the great geological forces that shaped the ancient supercontinent. The climate changes we're currently experiencing, while rapid by geological standards, are part of a continuous process of environmental change that has characterized our planet throughout its history. The difference is that for the first time, a single species has become capable of consciously directing the course of that change. The decisions we make about energy use, land management, and biodiversity conservation will influence the trajectory of life on Earth for millions of years to come. The technologies we're developing for space exploration and planetary engineering draw inspiration from the natural experiments that occurred during Pangea's time. The organisms that survived in the harsh interior climates of the supercontinent provide models for life support systems that might be needed for long-term space missions. The biogeochemical processes that maintained atmospheric stability during periods of extreme volcanism offer insights into potential approaches for managing planetary atmospheres. The genetic engineering techniques that are revolutionizing medicine and agriculture build on evolutionary innovations that first appeared during Pangea's existence. The metabolic pathways, structural proteins, and regulatory mechanisms that allowed life to thrive under ancient extreme conditions provide templates for designing organisms that can address modern challenges, from pollution cleanup to sustainable energy production. The conservation strategies we need to preserve biodiversity in a rapidly changing world can learn from the patterns of survival and extinction that characterized Pangea's mass extinction events. The species that survived these ancient catastrophes shared certain characteristics, including broad environmental tolerances, effective dispersal abilities, and flexible behavioral repertoires. These traits remain important for survival in the modern world and should guide our efforts to protect vulnerable species and ecosystems. The restoration techniques we use to repair damaged ecosystems often involve recreating the ecological relationships that first evolved during Pangea's time. The partnerships between plants and mycorrhizal fungi, the predator-prey relationships that maintain ecosystem balance, and the nutrient cycling processes that support primary productivity all have deep evolutionary roots that inform modern restoration efforts. The agricultural systems that feed our growing human population depend on crops and livestock that were domesticated from wild ancestors whose evolutionary histories extend back to Pangean times. The genetic diversity preserved in wild relatives of crop plants represents an invaluable resource for developing varieties that can adapt to changing climate conditions and resist evolving pests and diseases. The medical discoveries that improve human health often involve understanding biological processes that first evolved during the challenging conditions of Pangea's existence. The immune system mechanisms that protect us from disease, the cellular repair processes that maintain our health, and the physiological adaptations that allow us to survive in diverse environments all have ancient origins that inform modern medical research. The materials science innovations that enable modern technology frequently draw inspiration from the structural solutions that evolved during Pangea's time. The composite materials in dinosaur bones, the adhesive systems in ancient marine organisms, and the optical structures in prehistoric eyes provide templates for engineering applications ranging from construction materials to electronic devices. The energy production methods that might power our future civilization can learn from the biological energy conversion systems that sustained life during Pangea's existence. The photosynthetic processes that captured solar energy, the chemosynthetic reactions that extracted energy from mineral sources, and the metabolic pathways that efficiently converted food into usable energy all represent potential models for sustainable energy technologies. As we look toward our planet's future, the story of Pangea reminds us that change is the only constant in Earth's history. The continents will continue their slow dance across the globe, eventually forming new supercontinents and creating new environments for life to explore. The species that inhabit our world will continue evolving, adapting to changing conditions and exploring new ecological possibilities. The climate system will continue fluctuating, driven by complex interactions between geological, biological, and astronomical factors. But unlike the organisms that lived during Pangea's time, we have the unprecedented ability to understand these processes and potentially influence their outcomes. The scientific knowledge we've gained about deep time and ancient environments gives us tools for predicting and perhaps managing future changes. The technological capabilities we're developing might allow us to maintain favorable conditions for life even as natural systems continue their eternal transformations. The perspective we gain from studying Pangea's deep history encourages both humility and hope. Humility because it reminds us that we're part of a vast ongoing story that extends far beyond human timescales and priorities. Hope because it demonstrates that life has repeatedly overcome seemingly impossible challenges and found ways to flourish in the most unlikely circumstances. The organisms that survived Pangea's mass extinctions weren't necessarily the largest, strongest, or most sophisticated of their time. Instead, they were often the most adaptable, the most cooperative, and the most innovative in finding solutions to novel problems. These qualities remain important for success in our rapidly changing modern world, whether we're talking about individual organisms, human communities, or our species as a whole. The fossil record of Pangea's time shows us that evolution is fundamentally creative, constantly generating new solutions to environmental challenges and exploring previously unknown possibilities for life. This creativity isn't random, but represents the outcome of countless experiments in survival, each one building on previous innovations and testing new approaches to the fundamental challenges of existence. The ecological relationships that sustained life during Pangea's existence demonstrate the importance of cooperation and mutual dependence in creating stable, productive biological communities. The organisms that thrived weren't those that could dominate their environment through force alone, but those that could form beneficial partnerships with other species and contribute to the overall health and resilience of their ecosystems. The evolutionary innovations that allowed life to colonize previously uninhabitable environments during Pangea's time show us that apparent limitations often represent opportunities for creative solutions. The extreme aridity of the supercontinent's interior drove the evolution of sophisticated water conservation mechanisms. The massive size of Pangean predators led to the development of new defensive strategies and social behaviors. The instability of late Permian climate conditions selected for organisms with unprecedented physiological flexibility. These lessons from deep time suggest that our current environmental challenges, while serious and unprecedented in their rapidity, also represent opportunities for innovation and adaptation. The same creative processes that allowed life to flourish during Pangea's existence continue to operate today, though now they include human consciousness and technology as new factors in the evolutionary equation. The story of Pangea ultimately teaches us that our planet is a living system where geology, climate, and biology are intimately interconnected. The movements of continents influence the evolution of life, which in turn affects atmospheric composition and climate patterns, which then influence geological processes in an endless cycle of feedback and adaptation. Understanding these connections helps us appreciate our role as both products and agents of this ongoing evolutionary process. As the night grows later and these ancient landscapes fade into the realm of dreams, we can find comfort in knowing that we're part of a story that extends far beyond our individual lives or even our species' existence. The same forces that shaped Pangea continue to operate today, creating new possibilities for life and consciousness to explore. The same creativity that allowed organisms to survive the greatest catastrophes in Earth's history remains available to us as we face the challenges of our rapidly changing world. The continents continue their slow dance, the oceans keep circulating heat and nutrients around the globe, and life keeps finding new ways to flourish in an ever-changing world. Whether we're truck drivers navigating modern highways built on ancient foundations, students learning about the deep connections between past and present, or simply curious individuals wondering about our place in the cosmic story, we're all participants in the ongoing saga that began long before Pangea, will continue long after our current continental configuration has given way to whatever comes next. The next time you see a mountain range, remember that it might represent the suture where ancient continents collided during Pangea's formation. When you observe the ocean, consider that its basin might have opened as the supercontinent split apart. When you encounter a bird, recall that its ancestors first took flight when continents were drifting toward their current positions. These connections between past and present, between the vast scales of geological time and the immediate reality of our daily lives, remind us that we're part of something much larger and more wonderful than we often realize. And so our journey through time draws toward its close, though the story itself continues forever. The ancient world of Pangea has given way to our modern Earth, but the same processes of change, adaptation, and innovation that characterize the supercontinent's era continue today. In our dreams tonight, perhaps we'll visit those ancient landscapes, walk among the enormous dinosaurs, sail the vast Panthalasan waters, or soar above the breaking continents as they begin their journey toward our familiar world. The story of Pangea reminds us that our planet has a deep history filled with wonder, challenge, and transformation. From the formation of the supercontinent through its gradual dissolution, from the rise of complex life to the catastrophic extinctions that cleared the way for new evolutionary experiments, the ancient world offers lessons about resilience, adaptation, and the endless creativity of life itself. As we rest tonight, we can take comfort in knowing that we're part of this continuing story, contributors to the next chapter in Earth's ongoing evolution. The challenges we face today are part of the same grand narrative that includes Pangea's rise and fall and the same qualities that allowed life to flourish during those ancient times. Creativity, cooperation, and adaptability remain our best tools for building a positive future for our planet and all its inhabitants. Sweet dreams, fellow travelers through time. May your rest be peaceful and your dreams filled with the wonders of our planet's extraordinary past, present, and future.